Okay. Hello, everyone. So this is me, Aditya. I'm a research scientist at Hewlett Packard Labs in Hewlett Packard Enterprise in Milpitas. We have started doing some of this spatial sharing of GPU with Parsl project together with Logan and Kyle and Ian. And I will present some of the initial findings and some of the initial techniques we have used to do GPU multiplexing with Parsl. So first, the motivation is the GPU is not always utilized fully. So mostly in case of inference and other things, where you have a target, where you have a deadline of some hundreds of milliseconds or less than 100 milliseconds to hit, then you cannot really batch a lot. So in those cases, even a single GPU might not be utilized. So what we did was like we checked Llama 2, and then we saw that as we increase, the x-axis shows the number of streaming multiprocessor or amount of compute of a GPU. As we increase it, we see like after a point, like quite easily, like you will see there's no improvement on the inference latency. It remains the same. So also what we saw with some of this convolutional model, like DenseNet, ResNet, or RexNet, the image recognition model, we saw that some of the kernels utilize a lot of flops. They have a very high flops count, millions of multiplication, but most of them are pretty low down here. That means like they are not, a lot of kernels are not fully utilizing the GPU at all. So one of the things that we could think of is why don't we use run multiple things in the GPU together? And that is like what everybody would do, but the multiplexing of GPU is kind of tricky. If you just run it together without any support of MPS or MIGs, you will be time sharing the GPU, especially in NVIDIA GPU, and then you saw like providing the entire GPU for the single function might not be cost effective. So what we have is we have the solutions like MPS or MIGs that lets the user share the GPU. If you see on the right side, there is this is a V100 GPU, 80 SMs. You can give like what percentage of SMs you want to give a certain application, and it will use that much. It will just, it will not exceed that barrier that only use that many SMs. So you're basically provisioning a resource for something. So, and the new technical MIG or multi-instance GPU has also come, which have a predefined smaller instance of GPU. Like you have H100, you can either divide into 7 of like 10 gigabytes memory each, or 4 of 20 gigabytes memory each, or you can mix and match. Similar options are also available for A100. And they are more tuned towards not just spatial sharing, also for the privacy preservation, like application cannot look at the other MIG instance memory and so on. In MPS alone, there is no memory isolation. So AMD also has something similar, not I would say not as intuitive to use as NVIDIA has, but they also allow spatial sharing in many cases. Now, what we did was like we did not really in this project we haven't really worked beyond like a single GPU. What we did was we just took Parsl, and then we modified some of the high throughput executor of the Parsl, or high throughput executor in the Parsl, so we can define like which GPU we want to use as with the GPU ID. That is already present option, and you can also define the added option is like what GPU percentage you want to use on each of those GPU. So when the function launches, and if it launches on the certain GPU ID, it will only use that much GPU percentage. So as in like in this case, there is a GPU ID 0. There's 2 times that. It means like each GPU ID 0, the function will take 40% of the GPU ID 0. So in the background, what this really does is it's quite simple. When the function is being launched, when the process is being created, it just populates the environmental variable called CUDA MPS active thread percentage. This is the variable that activates the GPU percentage that user defines. And in case of MIG, that is the multi-instance GPU, it is even easier. The MIG has to be created by the user beforehand by some kind of script or manually. But what MIG does is like MIG gives pretty much an ID similar to what a GPU device ID would be. It is called a MIG ID. And then you can, rather than putting a GPU ID there, the 0, 1, 2, 3, 4, you can just put a MIG ID, like MIG1, MIG2, or MIG3, whatever. And then the functions will just run on those particular MIGs. Just a test case, what we did was like we took a Llama code, we put it as a function in concax, and we ran it on one A100 GPU. Since we only were targeting only one GPU right now, so we only took the smallest version of Llama. And then the task was like 100 text completion. There's a paragraph, and the model has to complete the text. And when multiple Llamas processes are running, each process get a fraction of 100 text completion. So if you're running two, we're giving 50-50 text completion to each of them. So what we saw was like one process running at the MIG or at MPS or at any default is the same. It probably takes around the same amount of time because only one instance of Llama is running. But when you start increasing the number of processes, then you see that this MIG and MPS start making a lot of dent. Like they have higher throughput. And so therefore, like you will, as you run 4, you get like 60% lower task completion time. And similar thing, well, if you look at the latency, while running MIG and MPS, you'll see a little bit of latency increase compared to the time setting, which is default. So this project being like very, very, very initial results and things. So what we have thought, like there are many directions that we could go, which we will explore in future, is this currently is very static. Like you are putting a GPU percentage before something comes up, and then you're just living with it. How to dynamically allocate GPU percentages, how to multiplex, have different multiplexing strategies. And then another is like you have to reload the model again and again, or reload the process again and again to change the GPU percentage. How to be able to keep the resources in GPU, and how to go beyond the implementation of single compute node, as well as, like there are many multiplexing where pipelining makes more sense than just concurrently executing. We saw some of the examples like that. So these are the next steps that we have been thinking. Thank you very much. It was a great pleasure to share this with you. I can get questions.
Thank you. Questions?
Is this implementation available anywhere?
We have not open sourced it yet, unfortunately. We have the paper, workshop paper in SC workshop ROS that has pretty much fairly written like what have been changed in the throughput executor part.
Question? Yeah, have you evaluated the difference between many parallel processes on the GPU and then just increasing the batch size? You can get the same performance just from throughput from maximizing batch size. How does that compare to this approach?
Yes, so that is a very, very valid question. Is if you can increase the batch size and if you can saturate the GPU, of course, like there's no point in really sharing it because you have actually occupied, you have actually be able to utilize the GPU fully. But we have seen like we ran some workflows, basically some of the LAMPS workflows where we found out that some kernels are taking an entire GPU, but there are still points in execution where the GPU is not being fully utilized at all. So in those cases, like we can, even in a small few milliseconds, we can probably be able to share the GPU. That is our thought. But yeah, if you can fully saturate with some kind of mathematical multiplication, matrix multiplication alone, then the sharing doesn't really make sense in those cases.
Thank you.